So we're going to start chapter 3 today, and chapter 3 talks about quadratic functions. This section in particular, we're going to be looking at quadratic functions and inequalities from a little bit different perspective. What we've done so far is sort of grouped quadratic functions in with polynomials, and mostly what we've done with them is either graph them, like graphing parabolas, we've done that, or we have factored them, set them equal to 0, and solved them. Those are the things we've done so far. So we're going to shift our focus a little bit and talk a little bit more specifically about these types of functions today. So a quadratic function has a general form, and that general form is y equals ax squared plus bx plus c. In particular, the a at the very front has a name. I'm not going to ask you the name, but it's called the amplitude. And it talks about how the graph opens. So if the a value is positive, it's an opening up parabola. If the a value is negative, it opens down. And that should make sense from the things that we have done back in the section about shifting graphs around, right? About reflecting things over the x-axis, that kind of stuff. It goes right hand in hand with that. The vertex, which is that lowest value, like this, or the highest one, if it's opening downward, is actually found in a couple of different ways. The way that we're going to find it first is with the vertex formula. And you'll notice that it kind of looks a little bit like part of your quadratic formula, which kind of should make sense because we're working with quadratic equations. It's the part that doesn't have the square root. Negative b plus or minus the radical over 2a. Well, if you eliminate the plus or minus the radical, that's what you have here, negative b over 2a. Okay, that's where it's coming from. And then the piece over here, which looks a little daunting, is simply saying that if I take that x value and plug it back into the equation, I find the corresponding y value. So in other words, if using this I found out that x is equal to 3, I could plug it back in here for x, and I could find y. And that's all that second box says, is that's how I find y. The last piece talks about something called the axis of symmetry, and the axis of symmetry is just a vertical line that cuts the graph in half. So visually speaking, from what I've drawn so far on these here, it would be this line that goes straight through the vertex, right? It cuts the graph into half, so it's matching pieces on either side of that dotted yellow line. That's the axis of symmetry. And of course, it's the same x value that we had gotten for the vertex because it's going through that same x place. So we're going to do some examples with this now. In particular, on number 1, we're simply going to find the vertex. So this is just an application of that formula. So x equals negative b over 2a is where we're starting. So looking at this equation here, what's my b value? Negative 8. So if you want to just write 8 on top, you can. If you want to write the negative that's there and then put the negative 8 in, just for the time being to remind yourself where this is going, you can do that. And we're dividing by 2 times a, and what's a? Negative 2. Got lots of negatives in this problem, don't we? Yeah, so the negative 2 at the very beginning. So clearly, like we just said, the opposite of negative 8, if you didn't do it already, would be just 8. What do we have on the denominator? Negative 4. And what is 8 divided by negative 4? Negative 2. So that's the x value, right? Just putting the x next to it as a reminder. We still need to get the y value. And then we get the y value by taking the equation that we already have and putting the x value in. So negative 2 times negative 2 squared minus 8 times negative 2 plus 9. All right, so we're going to simplify that expression that we have all there on the right-hand side now. So obviously this piece right here where it says negative 2 squared, right, all of that, ends up being 4. So we have that as 4 here times the negative 2 in front, so that's negative 8. In the middle I have negative 8 minus 2, which is 16. And then I have plus 9. You don't have to write all those pieces down, but I didn't want to grab a calculator. If you wanted to grab a calculator or you want to do it real quick on scratch paper or in your head, that's fine. Adding all of those pieces and so forth together, what will we get? 17. Okay, everybody good with that? And that was y. So my vertex is always an ordered pair. It's an xy point. So I need to make sure that my answer is written that way. It's the point -2, 17. Okay. On the next one, it asks for much the same question, different equation, of course, but it also asks for this additional sort of thing that says axis of symmetry. But finding the axis of symmetry is exactly the same as finding the x value of the vertex. So it doesn't change what I'm being asked for. I'm just going to have two answers. So I've got x equals -b over 2a. So using this equation now, what is b? It's 2. And what is a? -1. So on this one, I have -2 over 2 times -1. So it's -2 over -2, which is 1. Now with the axis of symmetry, you'll notice over here, the axis of symmetry is not given as an ordered pair because it's not. It's a vertical line. A vertical line is written as x equals the value that the vertical line crosses through, right? All the x values. So this answer is not vertical asymptote is 1. The vertical asymptote is x equals 1. That's it. You've got to have the x equals part, or it's not a line. It's just a number. But the cool thing is that gives me half of my vertex already. So when I give my vertex down here, I already know the 1 comma, part of it, the first piece. I just need to find the corresponding y value. So my y value will be taking the x value of 1 and evaluating it into the equation I was given. So I have -1 squared plus 2 times 1 minus 6. So this is just -1 plus 2 minus 6. What will that give me? -5, yeah. So my y value is -5. So my vertex is 1, -5. Okay, so far so good? Yes, Elizabeth. Of the vertex. Yep, the axis of symmetry is just the x value of the vertex. So when we're asked for both of those things as opposed to just finding the vertex, we're really not asked to do anything different. We're just asked to state an additional fact. So we're taking things a little further. We're going to do a few more pieces of information. Basically, we're going to take what we've already been doing, and we're going to combine it with some of the things that we've done before. So we're going to find the y-intercept and the x-intercept. We've done that before. We're going to take a look at the direction in which it opens. So taking this equation that we already had, the direction at which it opens, and we're going to graph it. And then after we've graphed it, we're going to find where it's increasing and it's decreasing and its domain and its range. So this is just a continuation of this particular problem we already have, but adding on things that we've already done. All right, so if you want, you can actually take the pieces we've already created, which is that we have a vertex at 1, -5, and you can actually plot it. So here's 1, -5. So my graph will have a point here. And you can also draw in the axis of symmetry. It's like this. So those are the two pieces of information so far that we did from parts A and B. The vertex and the axis of symmetry. Part C says we're going to find the y-intercept. So if you remember, the y-intercept is when x equals 0, and the x-intercept is when y equals 0. That's what we're looking for in each of those. Letting x equal 0 is the easier of the two things to do, because if x is equal to 0, we get a lot of zeros on the right-hand side, right? And it all simplifies to what? Oh, thank you. Got my sign off, -6. So it all simplifies to that -6, right? So what is my y-intercept? Well, let me erase this because I don't have any space for it. But my y-intercept is an x value of 0 and a y value of -6. So on my graph, I could plot that. That would be here. X is 0 and y is -6. Okay, that's my y-intercept. My x-intercept is when y is equal to 0. So I have 0 equals -y² plus 2x minus 6. There's a couple of things that you could do at this point. You can try and factor it. That's fine. You can do a quadratic formula. That's fine as well. But I'm going to suggest we pause for a moment on this one specifically and take a look down at part E, and then I'm going to come back up to part D and answer it without doing any work. That sounds good, right? What's the answer to E? What is the direction in which this parabola opens? It opens down. Why does it open down, Levi?
Constant before the x squared is negative.
You got it. Constant before the x squared is negative. So this is going to open downward. Now I know it's going to connect these 2 points like this when it opens downward. So what can you tell me about the places where it's going to cross the x-axis? Say it louder, Tiffany. There are none. Right? And if you were to try to factor, and if you were to try to do the quadratic formula, you would find this same thing. In particular, if you try to factor, it's not going to factor. If you try to do the quadratic formula, you're going to end up with a negative underneath that radical. Negative underneath the radical creates some imaginary values, but they don't show up on a real number line graph, right? They're not going to. They're not going to show up there. So there are none here. And we can base that upon the fact that those other pieces have already forced it to happen that way. Now, if this were opening upward, we wouldn't get that luxury. We would be continuing on with some algebra to simplify and all that stuff, either factor or quadratic formula to find those x-intercepts. But there are no y-intercepts. Are no x-intercepts, on this one. We've actually graphed half of this. The axis of symmetry is a mirroring line. So we've graphed the left half, right, where it's going downward. And if I mirror it over to the right-hand side, I'll have the same piece over here. That was not a very nice mirror, but that's not too bad. This would be the rough graph for it. Okay, and we did it using symmetry, is what we really did. That line, the symmetry through the axis of symmetry. So we should be able to now look at this and answer questions about decreasing, increasing, domain, and range. So let's just go in order as they're listed. Where is this graph increasing? Huh? It is increasing somewhere. On the negative side, the left side, right? So it starts at negative infinity. Where does it stop increasing? At 1, namely the vertex on this one, yeah? So my graph has the the interval where it's increasing is negative infinity to 1. How about the graph decreasing? 1 to infinity. Lovely. Domain. Domain means walking from the left to the right-hand side of the graph. What's my domain? I get the whole thing, negative infinity to infinity. How about my range? Good. So negative infinity, I start at the bottom of the graph, and I travel upwards until I get to the y value of the vertex, which is actually at negative 5. And that's the location where it turns around and goes back downward, so I have negative infinity to negative 5. Okay, so we're just piecing together everything that we've been doing with this one additional piece of information about axis of symmetry and vertex. Yes, so sorry. You're right. Let me get that in there right. Good grief. Should be. Thank you. That's the only one that we need to bracket on, but it is, yes. All right, so this over here was the general form of a quadratic function, right? ax squared plus bx plus c. But we also have something called the standard form of a quadratic function. And I don't care that you know that one's general and one's standard. They're used in different fashions for different things, but I'm not going to ask. It's not a trick question I'm going to figure out to ask you. That's not my goal, okay? So the standard form actually gives us the form in which it looks more like what we did when we shifted graphs around, like we moved up, down, left, and right. Like if you look at the equations that are given in this form, you can't see how it's been shifted or adjusted from the original x squared graph, right? With the exception of the fact that it would maybe be reflected up or reflected down. You can't see any shifts. But when we look at the general form, the standard form, the other one, you actually can see them. So the standard form is y equals a times x minus h squared plus k. We've seen this before. Okay, the a would flip it upside down and right side up, but it also stretches it out of shape, makes it either really skinny or really fat. What does the h do? Left and right, depending on its value, right? The h moves the graph left or right. What's the k do? Moves it up and down. So actually, it's nicer, it's easier, it's much easier to graph if I have it in this form than if I have it in the other form. Now, one thing that's not quite as nice is it's not quite as nice to find the x and the y-intercepts. It's just not as friendly. But you can find the vertex, you can find how it's been shifted left, right, up, and down, really nice. The a value at the front still is the amplitude. If it's positive, it opens up. If it's negative, it opens down. The really cool thing here on this for the vertex is that while it's true that the vertex is negative b over 2a, like we did before, I don't really need that here, because you can actually see the vertex already in the problem. It's hk, the same hk that's showing up there. So it's an identification problem, not a solving kind of problem. And then your axis of symmetry is simply the x value of the vertex, just like before. So if we're given an equation, this is an example of one, it's given to us in general form. And we could do exactly like what we did before, and it wouldn't be wrong. The directions don't ask us to do that on this one, so sort of by the nature of the directions, it's not what's being asked to do. It's asking you to first put it in standard form. So standard form was this one, a times x plus h squared minus k, or plus k. Right? That's what I'm looking for. So how do I do that? Well, it's something you guys still don't like, and we've done it twice. It's called completing the square. Yeah, we're right back there. So we're going to give it a go. So here's how it works. You have your y equals, you have your x squared minus 6x, and you're going to leave a space, and then you're going to put your 10 on the outside, and these three pieces are going to go in parentheses, just like they did when we found the center of a circle. And you're going to take that middle term, negative 6, and you're going to divide it by 2, and you're going to square it. It didn't go away, even if you didn't get it right on the test. It's still here. What is negative 6 divided by 2? Negative 3. And negative 3 squared is 9. So we're going to put a plus 9 right here. So what did we do? We did negative 6 divided by 2 squared. Gave us a 9. Now there's a caveat to doing this. In a minute we'll encounter it. But for right now, we've done everything we're supposed to do. There's one thing we have to do when we did circles. Do you remember when we just added 25 to the left? We had to also add 25 to the right. Do you remember doing that? Right? It's a balancing act. It's compensation. If I add something to the left, I have to add something to the right, or vice versa. Well, I don't really want to add anything over here with y. That's not super helpful. But I still have to balance. And so the way that I balance without adding something to the left, in this case, is that since I added it to the right, I also subtract it from the right. Well, that should make sense, right? You add something in, you take something out. So we simplify. The part that's right here, as always, will always factor perfect squares. The factoring for quadratic, or for completing the square, is always wonderful, always. So we take the first term and we take the square root. Well, the square root of x squared is x. We take the last term and we take the square root. The square root of 9 is 3. We take the sign of what's going on in the middle. It's a negative. And we put the square on the outside. And it always has that form. So factoring of it is always very friendly. And then we add the pieces together that are on this outside. So I have positive 10 and negative 9, so that's a 1. Yes?
Since it's negative 6 divided by 2 is negative 3, would the middle sign of the constant?
The middle sign always matches the original piece. So you get something from each of the pieces.
Is it minus negative 3?
No, it just takes whatever sign is already there.
Oh,
So if the sign is negative on your middle term, then the sign in between the two pieces in your factoring is negative. And if the sign were positive, it'd be positive. Yeah, it just keeps the sign. So this is actually the standard form we were looking for. We've done what we've been asked to do. The second thing it asked us to do is to find the vertex. Well, again, we don't have to work for the vertex because we worked to put it into this form. The vertex we get for free. It comes from these locations where H and K are. Now, Noah, you're asking about the sign. You do have to switch the sign for the vertex. So on the vertex over here, notice I have x minus h. We talked when we looked at transforming functions, that moves it to the right h if h is positive, right? Well, that's what's going on here. This is x minus 3. It moves it to the right 3. So my vertex is not at negative 3. It's at positive 3 and then 1 because it moved it right 3. So the sign is opposite of what you would expect sort of it to be from the middle term. But the sign on the outside is the same, right? We moved it right 3, we moved it up 1. Well, my vertex would now be at 3, 1. Okay, so there's some other pieces, maybe not. No, we're going to do another one that has the other pieces. So we're going to do kind of the same thing we did before, but we're going to do it from the perspective of having a formula that's given to us in standard form instead of in general form. And we're going to find all the pieces basically that we found when it was given to us in general form. So all the pieces are there, but we work with them in a slightly different way because the form starts out looking slightly different. This one wants us to find several things. The form is already given to us correctly. We don't have to work to get the form already. It's there. So I have this as my equation. What is the axis of symmetry? Okay, so nobody told me x equals, and that's the first important part. Axis of symmetries are lines. It's a vertical line, so it's x equals. And then I think I heard both x equals 1 and x equals negative 1. Which one is it, 1 or negative 1?
Negative.
It's negative 1. Why, Levi?
With the positive or the plus one inside parentheses moves it left.
Yeah, it's exactly right. That plus 1 inside the parentheses moves it left 1, so my axis moves left 1 as well. So it is at x equal negative 1. And likewise, then my vertex will also have the component of negative 1. And what will the y component be for my vertex? Negative 9. So those are easy to find because of the way the form is given. Y-intercept and x-intercept may or may not be. Let's actually plot what we currently have. So I have negative 1 and I have negative 9. Looks like that. And I have my axis of symmetry. And it looks like this. You don't have to put in your axis of symmetry, but it's often nice to see it there so that we can use symmetry to redraw graphs and things like that the other side of them when they show up. Now, you always have, with parabolas, a y-intercept. That will always happen, okay? It's just that you may or may not have an x-intercept, right? Like we had one over here where there's no x-intercept because it is opening downward and it's all completely underneath the graph of, or the x-axis, right? So that can happen. But you still always cross the y-axis. So as we're taking a look at the y-intercept, that's the locations when x equals 0, and that will always have a value. So this is y equals, this is 0 plus 1 squared minus 9. So we simplify. 0 plus 1 is 1, 1 squared is 1, and then minus 9 would give me negative 8. So if you were asked to list this, the listing would be that x is 0 and y is negative 8. It is an ordered pair. And if you're asked to graph that, that's right here. Now, it kind of looks like I'm graphing the same thing I did over here, doesn't it? I've got this vertical line drawn. It's just drawn on the left. I've got, see these 2 points? But it's not actually quite the same. And I'm going to skip the x-intercepts for a moment to sort of verify that we really do have to find them. What's the direction in which this graph opens? This one opens up. And we identify that it opens up because the number in front of here is an understood 1, and that 1's positive. It will open up. And since it opens up, it is going to cross the x-axis. Right? And I can draw one more point from the symmetry that I know from the axis of symmetry if you wish. I could actually draw the point that goes to the left one of the axis of symmetry and up one as well, because that's what happened to get me my y-intercept. So if you want to draw that additional point. Now, we still have to go back and find our actual x-intercepts because we actually have them this time. We don't get to just say they don't exist. That was nice on the last one, but not so nice on this one. And honestly, this solves a little bit differently. So my x-intercept is when y is equal to 0. So y is equal to 0 means I have 0 equals x plus 1 squared minus 9. There's some options. If you want to, you can distribute this out and simplify it. I don't think that's your easiest choice. This actually sets up really nice to be solved with the square root principle, which you guys did pretty well on your test, with the exception of the pluses or minuses that some people missed. So what do I mean by the square root principle? Let me shift this opening upward down here so that I have some more space to work. Well, it means I can add the 9 to the other side. So 9 is equal to x plus 1 squared. So I have something squared on one side equals to a constant on the other side, and I can square root. So the square and the square root here cancel, leaving me with simply x plus 1. The square root of 9 is 3, but it is plus or minus when I put the square root on, right? So I have x plus 1 is equal to positive 3 and negative 3. That's two different equations. X plus 1 is equal to 3. X plus 1 is equal to negative 3. And in both of those equations, I have to subtract 1 in order to solve it for x. Agreed? So then what is 3 minus 1? 2. And what is negative 3 minus 1? Negative 4. Now remember, these are ordered pairs. So my x-intercepts are y is 0, but now I have x is 2 and x is negative 4. These are my two y-intercepts. Is that all right? We should be able to plot those now. So I've got 2, 0. And I've got negative 4, 0. And again, if you look at the symmetry, it should make sense. I should be spaced the same distance apart from the axis of symmetry. 1, 2, 3 to the right. 1, 2, 3 to the left. Right? That makes sense. There's got to be symmetry around that. And I can actually connect all my dots, and I got a bunch of dots this time to connect. That wasn't good. It's not too bad. So there's my graph. From that graph, I should be able to identify where it's increasing, decreasing, and if I were asked, I could do domain and range. I don't know if I am on the next page or not. Nope. So this one just wants me to do the increasing and decreasing part. So where is this graph increasing? Negative 1 to infinity, so the right-hand side this time. And where is it decreasing? Right, negative infinity to negative 1. So it's decreasing right here, and it's increasing, that's not going to show up, right here. Right? Excellent. Any questions on those? All right, so we're going to work a little bit more with standard form of the vertex, standard form and finding the vertex, excuse me, because they don't always work out beautiful. I mean, they don't. But the factoring part of it is nice, even when they don't work out to being ideal. So when we're finding the standard form, we always take our x squared minus x, whatever we have, we leave a space, and we, sort of boot the constant out. It does not get to be included in the parenthesis to start with. And I need a value using this number, and it's not written in there, but it's a -1. So my key value is to take the middle value, that -1, divide by 2, and square it. So what is -1 divided by 2? It's -1/2, right? What is -1/2 squared? 1/4. So I add the 1/4 on the inside, and I compensate by subtracting the 1/4 on the outside. So again, even though this isn't pretty, it always has the same forms of factoring. The first term is x. The last term is the square root of 1/4. That's 1/2. And the middle term keeps the same sign, or the middle of it keeps the same sign, so it's a negative, and we put a square on the outside. Now I need to know what is 1 minus 1/4. 3/4. Hopefully you're thinking quarters. Right? $1 minus a quarter is 3/4. So we end up with this as the standard form. And then what would be my vertex from that equation? Yep, 1/2, sign's opposite. 3/4, the sign's the same. Okay, so I mentioned earlier there is one caveat that I hadn't encountered with you yet. It wasn't this. This is something we've actually seen done before. We did this once before when we were solving quadratics. But we didn't see this, and this is different. How does this really look different than the other two that we've done? Say that louder. It has a constant that's not 1, right, in front of the x squared. Do you guys see that? Yeah, that actually creates a problem. So it's not a huge problem, but it can't stay there. So when I create my parentheses have to keep the 3 on the outside, just like it keeps this +1 on the outside. But what it means is that I have to take the 3 out of, right, factor it out of what's going to go inside the parentheses. So the 3x squared would just be x squared. That's fine. But I have to do it to the 12x, -12x, as well. So if I take -12x and I factor out a 3, what do I have? Yeah, I have -4. Okay, so that's the first way in which it affects things. There's one more in a moment. What we're about to do now is just like before. I take the middle term, that -4. I divide it by 2 and I square it. Notice I do it with a -4, not with the -12 that I originally had. That's important. So what is -4 divided by 2? -2 squared is 4. So I'm going to add 4 right here. But I don't actually just do subtraction of 4 on the outside. Because that 4 that I added in that parentheses is also multiplied by the 3 that's in front, right? Right? I pulled it out of the 12. I pulled it out of the 3. Well, when I put the 4 in there, I've automatically already pulled it out of the 4 that's in there as well. So when I added this 4, I really added 3 times 4, which is 12. So my compensation is to subtract a 12 on the outside. That's different. I didn't have to do that before. The rest of it works out very much the same way. 1 minus 12 is -11. I do my factoring the same way. The square root of x squared is x. The square root of 4 is 2. The sign between is a negative, and it looks like this. The 3 just makes the graph narrower, right? It makes it skinny. It's a vertical stretch. So we're making something look like, do you guys know who Gumby is? Oh, that's a no. Oh, I got a couple nods. Like, imagine, these Play-Doh things people have or whatever, and you just stretch him up and he makes him tall and skinny. Okay, that's Gumby. Google it later. You'll know. At any rate, this is my standard form. And then my vertex would be what?
Would be negative 6, or 611.
Okay, so the negative 11's right, but it's not 6. It's 2. So it stays whatever's inside, whether or not there's a 3 or not at the front. So that won't affect it. The 3 will affect it stretching up, but it doesn't affect where the vertex actually starts. So I have 2, negative 11. All right, the last thing we're going to look at in this section is inequalities. And if I have time for just one of them, I'll put the other one out right after class for you to go back and watch the last few minutes of. But we're going to take a look at solving quadratic inequalities, and this is called the test point method. So basically what we have is we're going to move everything to one side of the equation. We're going to factor. All that just sounds like what we do with equations anyway. And then on step 3, we're going to test using intervals and check using intervals and test points. And the last thing is we're going to find a solution. So the process itself is a little different than what we've done before because of those last couple of steps, the intervals and the solution part coming into play. So let me show you how it works. The first thing it said to do is move everything to the same side. So we have x squared plus x on the left. We have a 2 on the right. So the first thing I'm going to do is going to move my 2 to the left with the other stuff. So I have x squared plus x minus 2. Okay, so far so good? So the next thing I'm going to do is I'm going to factor that if I can, or quadratic formula if I can't. This one factors, and it factors really friendly. So I have x and x. The sign at the back is a negative, which means my signs have to not match, one positive and one negative. There's only 2 numbers that multiply to give me 2, 1 and 2. I just need to make sure I put them in the right spots. So is it 1, 2 or 2, 1? It is 2, 1, and the reason it's 2, 1 is because I need a positive 2 and a negative 1 to give me a positive x in the middle. And then what we do is we set each of these pieces equal to 0. Okay, so far we have not done anything with the fact that this is an inequality. Are you recognizing that? This looks exactly like the stuff we were doing back in chapter 2. So I subtract my 2, so x is equal to negative 2. I add my 1, and x is equal to 1. So all of that's the same so far. Those are not our solutions, though. All right? Those are places where it's equal to 0, not where it's greater than or equal to 0. So this is the part where steps 3 and 4 come into play. So we're going to draw a number line. Wow, not right there. We're going to draw a number line, and we're going to put the numbers on that we have in order. In particular, that means negative 2 has to come before 1. Okay? And then we're going to choose test points. So test points means that what I've done is I've split my graph into 3 areas. There's an area of the graph here, an area here, and an area here. Does that make sense? There's 3 different areas of my graph, and I need to figure out what's happening in each of those areas. Do I have a graph that's positive or do I have a graph that's negative? Because it has to be one of the 2. So we're going to test those 3 areas, and we can do that using test points. So all I need to do is I need to pick a value that's smaller than negative 2, and no matter what I pick, and what Kylie picks, and what Tori picks, and what Noah picks, it doesn't matter. We'll still get the same sign if we've done it all correctly. So I'm going to just pick negative 3. But you can pick negative anything you want over there, and it'll work. In between negative 2 and 1, I mean, really, is there anything else to pick but 0? I mean, there is, but 0 is nice, right? It's always nice to pick 0. And then I need to pick a number bigger than 1. I'm going to pick 2. Okay, you can pick other values as long as they're in the interval. It's still going to work. And what we're going to do is we're going to use those 3 values in the equation right here, and we're going to find out, is it positive or is it negative? So we put in this case, I'll start with negative 3. Negative 3 squared plus negative 3 minus 2. Well, what's negative 3 squared? 9. 9 minus 3 minus 2 It's something. I don't really care what the something is. I just care what the sign is. Is it positive or is it negative? Yeah, this is a positive number. That's why it doesn't matter what sign you pick or what number you picked. Your number value will be different, but your sign will still be positive. So right now I'm just going to put a plus right here on my graph, above it on the number line. I'm going to use my next test point, which is 0. So I have 0 squared plus 0 minus 2. What is that? Yeah, that's negative. So there's a negative right here. And the last one I chose was 2. 2 squared plus 2 minus 2. Lots of 2's. 2 squared is 4 plus 2 minus 2. And I get a positive. What do I want? I want greater than 0. So do I want the positives or do I want the negatives? The positives, right? So the parts of the graph that answer the question correctly are these outer edges. It's kind of like what happened when we did absolute value stuff, right? It is. And it doesn't always work out that it's the outside edges. It could be the the inner piece as well, right? If this said less than or equal to 0, our answer would be the trapped piece in the middle. But our solution is read much the same way. This would be negative infinity until we get to negative 2, and then it pauses. I'll put the parentheses and so forth on in a minute. Then it picks up at 1 and it goes out to infinity. This said greater than or equal to 0. The or equal to means I'm using brackets on the values negative 2 and 1. And we always use parentheses when we're working with the infinities. Okay, so here's what's going to happen. I'm going to pause the video, and I'm going to let you guys leave. I may leave too if there's people waiting on the hallway. I'm going to record the last example. It's just a couple of minutes. It won't take me very long. I mean, maybe 5 minutes realistically. And I would encourage you, once it's posted, to watch that additional example as you're starting your homework so that you have one more example of this type to look at. Okay? All right, so our last example, number 7, has the exact same directions that we just did on number 6. And we'll notice the first one, the first thing to notice here is that this actually says this time less than 0. So the last one said greater than or equal to 0, so we were looking for positives. This one we will be looking for negatives. The other thing that makes this one different is, while I could let you struggle a little bit to figure it out, this isn't going to factor. I can't break down the 2 at the end and in any way get the 4 in the middle. So when that's the case, then it's not able to be factored. We're back to using the quadratic formula. So the quadratic formula to find those interval sort of location stop spots. So x equals negative b, so negative of negative 4, plus or minus the square root of b squared, which would be negative 4 squared, minus 4 times a is 1 and c is 2. And it divides by 2 times a, which is 1. So as we simplify and clean this up, I have a 4 on the outside, plus or minus the square root. Negative 4 squared would be 16. Minus 4 times 1 times 2, which would be minus 8. So we end up getting an 8 underneath there, which we'll write in a moment, over 2. So I have 4 plus or minus the square root of 8 over 2. 8 factors, right? It factors into 3 2's. So I'm looking for a pair of them to come out of a square root. This is 4 plus or minus 2 square root 2, and it's over 2. So since I have the 2's showing up here, here, and here, I can divide them all by 2, which will leave me with 2 plus or minus 1, or just square root of 2, 1 times the square root of 2. Now, because we need to know an approximation to be able to choose test points, I mean, I will have my number line. My number line will have these values on them. I mean, it will, right? It'll have 2 minus the square root of 2, because obviously that's smaller than 2 plus the square root of 2. But I kind of need to know approximately what those values are to make sense of them as well. So if you put them in your calculator just to get an approximation, this is approximately 0.6, and this one's approximately 3.4. And what that allows us to do is to choose test points that make sense. So right, 0.6 and 3.4, you need a number in between them. So like maybe number 1 or 2, something like that. The 0.6, I need a number before 0.6. Again, and when in doubt, I always use a 0 when I can. And then 3.4, I need a number bigger, so maybe you choose a 4. So those are my 3 test points that I'm going to be using. Let me shift those over just a little bit. And so we're going to put those numbers in. So we'll do the 0 first. So we have 0 squared minus 4 times 0 plus 2. So that's a bunch of zeros plus my 2, which gives me a positive. So I have a positive on the left. I'm going to use 1 now. So I have 1 squared minus 4 times 1 plus 2. So this is 1 minus 4 plus 2. That gives me a negative. And I've got a negative in the middle. And then my last one is that I have a 4 squared minus 4 times 4 plus 2. So 4 squared is 16 minus 4 times 4 happens to be another negative 16 then. And then plus 2 yields again a positive. You might be looking at this and saying, hey, look, the last time I did positive, negative, positive. This time it's positive, negative, positive. Is it always positive, negative, positive? The answer is no, it's not. It just worked out that way on this particular problem. However, I am looking for the negatives, which means this one has the trapped area as my answer instead of the outer areas. So while my solution is somewhere in between, right, the 0.6 and the 3.4 as approximations, I'm going to use the official exact answers for my interval. So my interval goes from 2 minus the square root of 2 to 2 plus the square root of 2. And you'll notice I put the parentheses on the edges instead of brackets because there is no equal sign right here.